Chapter 24, Video 5. Here we are going to look at the aromatic amines. How to make the aromatic amines. We saw in chapter 16, this is an aromatic amine. You start from the benzene, reacted with nitric acid, sulfuric acid mixture, is N2 plus. That replaces a hydrogen. You get a nitrobenzene, and you reduce it with tin and KCl, the second sodium hydroxide. You get that. In the place of tin, you can use zinc or stannous chloride. The next reactions of arylamines. In arylamines, you have an aromatic group, basically benzene ring. And also you have amino group. This is a primary amine. So this can react like a primary amine. This ring react like a benzene ring. We saw the reactions on chapter 16. All those reactions are possible. We are not going to look at all these reactions. Some of them we are going to look at. Reactions at the ring. The ring undergoes electrophilic substitution. But the guy who sits on the ring is CH-24. He's an orthopara director. So if we do a reaction, for example, this, we learned in chapter 16, we expect an ortho product and para product. But in fact, we are not going to get an ortho product or a para product. Instead of it, we are going to get a polysubstituted product. Why? That NH2 group is a powerful ring activator. As a result, a substitution occurs at all ortho positions and para positions in the same molecule. So you get one product because it is a powerful ring activator. How to prevent this polysubstitution? We have to make it as a less efficient group. How to make it? We are going to acylate the NH2 group. So the NH2 is this. If you take it and put an acyl group, you know what is a acyl group is. Acyl group is a carbonyl group attached to some alkyl group. So this is an electron withdrawing group. This nitrogen is an electron releasing group. You attach an electron withdrawing group to the electron releasing group. So the efficiency of the electron releasing group will be decreased. Then we will have only monosubstitution. For example, in this case, I take the aniline and treat it with this and acylated the nitrogen. So now this group is an orthopara director, but it is not a powerful because there is no NH2. The NH2 is this, but now we took the hydrogen off and put this group. This is an electron withdrawing group. It pulls it. This tries to push the electrons. So it becomes a less efficient, but still it is an orthopara. If we do the reaction, it happens at ortho position and para position. You get two products. But how to get back the NH2? If we simply treat it with water in presence of a base, the AC group and the OH goes away, and that hydrogen takes the place. Same thing. So you have to do it this way. We are going to look at the reactions that happens at the NH2 group in the amines. As I told you here, NH2 on it is a primary amine. You see, this is a primary amine. All the reactions we saw that the primary amine are possible except the Hofmann elimination. Because in this case, alpha, the beta has a double bond. It is very difficult to pull a hydrogen from any beta which has a double bond. So other reactions are possible. We are not going to repeat those reactions. We are going to look something unique that is possible in aromatic compounds. One is formation of the diazonium salts. So I have an aromatic primary amine. We reacted with nitrous acid and hydrochloric acid. Careful. This is nitric acid, HNO3 nitric acid. This is HNO2 is nitrous acid. With a HCl, that mixture reacts with the here and form this compound. This compound is a salt, you see, cation, anion. This is called a diazonium salt. In the diazonium salt, this cation is called a diazonium ion. In this reaction, if you want, instead of the HNO2, you can use NaNO2 or potassium nitrous. So instead of this one. So something about, what about the primary alkyl primary amine? They also contains the NH2 group. So they should also form the diazonium salt. Yes, this is a diazonium salt. Unfortunately, this diazonium salt is not stable. This breaks away this way and becomes a carbocation and the nitrogen. So we don't actually get the diazonium salt. It is immediately breaks down into a carbocation and then nitrogen. But in the case of the aromatic one, this one will not break down. Why not? If it does, just like you saw that, if it does, it should be a cation. This is aryl cation. That is least stable. That is not stable. So this reaction will not happen. So this is more stable. It stays that way. It will not break into carbocation. The second one, the diazonium ion, undergoes resonance. You see this has a lone pair, and this flows back here and becomes this, and then goes this. It shuttles between back and forth. So you can write the diazonium ion by any one of the two structures using. Look at carefully. If it is a double bond between the nitrogens, the N nitrogen has a positive charge. If it is a triple bond between the nitrogens, the middle nitrogen has the positive charge. We are going to look at some reactions of the diazonium salt or diazonium ion. First one is a diazonium coupling or diazo coupling. We are going to couple the diazonium ion with an aromatic ring. Here is the mechanism. This is a diazonium ion. I write it in this form. It is convenient. I treat it with another aromatic compound. But this group, which contains the lone pair, that means mostly electron releasing group, it may be a halogen or an NH2 group or OH group. They all have the lone pair on it, or OR groups. Some of them like that, the Y group. What will happen is this bond breaks and makes a bond with it because it is positive. So this flows in here, this flows here. So now diazonium ion is coupled with aromatic ring. But this is not stable. Why not? You see, the ring is non-aromatic. It was aromatic here. It becomes non-aromatic. So it is going to break. But you note this has a hydrogen there. We don't write it, that hydrogen from this. So now this is going to pull that back. This moves on. This flip in. And you get this compound. In this compound, we coupled diazonium ion with an aromatic ring. This is called a diazonium coupling. But what is the functional group in this compound, you see? And then a benzene ring. So this compound is called a azo compound. There are several azo compounds. You can change, you can substitute the hydrogens, one or more here. Similarly, you can substitute these hydrogens with some groups, and you can have OH here, OR here, Cl here. So you get different compounds. So this is called a azo compound. Azo compounds are highly colored, so they are used as a dyes. So one reaction, you know. The next one, there is a nucleophilic substitution at the diazonium ion. So we are going to see several of them. You take a diazonium ion, treat it with a cuprous chloride and potassium chloride mixture. The Cl minus replaces this, because this is a nucleophile Cl minus. It replaces the diazonium part. You get that chlorobenzene. If you react it with a cuprous bromide, potassium bromide, the Br minus replaces it. So you get the bromobenzene. It is a nucleophilic substitution. If you react it with the sodium iodide, the iodide replaces it. You get iodobenzene. If you use this one, the F minus replaces this one. So you get the fluorobenzene. If you react this with cupric cyanide and potassium cyanide, the Cn minus is going to replace it, a nucleophilic substitution. You get a nitrile. And then if you treat it with dihydrogen phosphate, the hydrogen H minus is going to replace it, so it is a benzene. If you react the diazonium ion with water in presence of cuprous oxide and cupric nitrate, this OH is going to replace that. So you get the phenol, replace this one. So the diazonium ions undergoes nucleophilic substitution and form different products. These are important in synthesis. I tie them together. I have a benzene ring, and we convert it into nitrobenzene and reduced it to amine. We learned it in chapter 16. We learned it again here. If you treat this one with nitrous acid and sulfuric acid, it becomes a diazonium chloride. And if you treat that diazonium ion with cuprous chloride and KCl, it becomes chlorobenzene. If you treat it with this bromobenzene, you can convert them into different. But here, if you convert that into a nitrile, if you want, you can convert this CN into COOH. We learned it in chapter 19 and 20. If you react it with the CN, this becomes COOH. If you reduce it with the lithium aluminum hydride, it becomes a primary amine. So this roadmap presents all the reactions we learned under the aryl amines and also gives an easy method to do some synthesis. Suppose if your compound this is given and you are asked to go here, you have to convert the nitrobenzene into amine, amine into diazonium, and diazonium to the nitrile. Nitrile, you have to reduce it. 1, 2, 3, 4 steps. So you can do different synthesis using this one. We did some reactions under the preparations. I did not do the mechanism. I called it Hofmann rearrangement, Curtis rearrangement. What is Hofmann rearrangement? This reaction is a Hofmann rearrangement. You take an amide and react it with a mixture of bromine, hydroxide in water. It becomes a primary amine. We call that reactions or Hofmann rearrangement. What is the mechanism of it? Actually, this is a 3-part mechanism. The part 1, the OH actually pulls the hydrogen from this and flip it. So the nitrogen becomes negative. And that reacts with the bromine and form this one. So the part 1, hydrogens on the nitrogen in the amide is substituted by the bromine. In part 2, we have a brominated amide. This is N-bromamide. We are going to react it with hydroxide. It is there in the reaction mixture. It goes and pulls the hydrogen and flip the bond and put the electrons on the nitrogen, and the halogen breaks away as B or minus. You see the nitrogen now have 2 lone pairs, but no charge. If you have time, you try to calculate the formal charge. It is 0. This is not a stable compound. This is formed. Immediately what happens, this R group breaks away from the carbonyl and it goes and attaches to the nitrogen, and this goes here and form this one. This is the rearrangement. This rearrangement is called Hofmann rearrangement. The spelling's correct? I think so. It's an important one because in the exam you have 1 step to draw the arrows. Sometimes you may see this kind of it. Be careful. So it becomes a this. This is alkali isocyanate. So I have it here, isocyanate. The next water in the solution is going to react it with the product of the step 2. I'm simplifying it. You see, this has a lone pair. I will actually make it this way. You get this. It is actually carboxylic acid and an amino group there. But the next moment, what will happen, this will break and get the hydrogen, and this goes there. It becomes a carbon dioxide, and you get a primary amine. The water hydrolyzes the isocyanate into carbomic acid. This is a carbomic acid that breaks down into a primary amine. So this is the mechanism of the Hofmann rearrangement. What is the mechanism of the Curtis rearrangement? You remember Curtis rearrangement? We take an acid chloride and first to treat it with NaN3, and then second step we treat it with water. It becomes a primary amine. We called it as a Curtis rearrangement. This is also three-part mechanism. So the first part, this is an azide. The N3 replaces the halogen. No, not that way. I'm sorry. This flips and I write the whole mechanism, not simple way. And then this comes back and kick this out. This is a substitution at carboxylic acid derivative. The azide group replaces the halogen. In part 1, in part 2, I write the structure of this, the N3, expanding it here. This step is more important. This breaks down into that one. How we are going to put the electrons on it. The lone pair from this flows in. And that is the double bond. One of them flows in here. And this one goes here. Look at it, what are the changes? So that becomes a nitrogen. And this becomes the same unstable one. There is no charge on it. And then we saw in the Hofmann rearrangement, this breaks away and bonds here, and this bonds here, formed alkyl isocyanate. So from this part of it, it is the same mechanism. The third part, isocyanate reacts with water, carbomic acid, just like in the same one. So pretty simple. So mechanism of the Gabriel synthesis, we can skip it. Good luck.